Great. So with that, I'm very excited to introduce our speaker today. I've been trying to get Irmak out here for a while now, but so Irmak used to work for a data science company called Datascope Analytics, based out of Chicago, and they were recently, maybe a year ago, close to a year ago, they were acquired by IDEO. And so Irmak is working there now as their design director, and he's going to be telling us about the intersection of deep learning and Matt Damon, and something about the coolest looking guy.
Yes, you're looking at him.
So, and so let's welcome Irmak.
Thank you. Thanks, Sean. Hi, everyone. Thank you very much for having me here. I'm really excited to talk here, and I'm going to talk about how deep learning reveals the essence of Matt Damon. That's the name of my talk. But really, the actual title of the talk is that I decided that my face looked kind of like a movie star's, and I wanted to prove that using deep learning. So today we're going to go on a journey to prove how handsome I am using deep learning. Okay, first of all, who do I think I am? Sean, thank you very much for that introduction. The reason I wanted to mention one thing just a little bit is that I'm a design director at IDEO focusing on our offering that we call augmented intelligence. We call it augmented intelligence. You can think of it as like a play on words, like artificial intelligence, AI, augmenting people's intelligence instead of replacing humans in a machine. Let's enhance their skills and capabilities. That's what we try to do. And actually, that's not that different from what was happening in the first heyday of Silicon Valley. And Steve Jobs said, the computer is the most remarkable tool we've ever come up with. It's the bicycle for our minds. What he was talking about was basically augmenting, computers augmenting people's intelligence, right? And actually, Steve Jobs and Microsoft, Apple, Bill Gates, they all kind of took inspiration from Xerox PARC, which is in the 50s, 60s, they were really developing how to augment human intelligence. This is way before deep learning became what it is today, but this whole augmenting intelligence thing is not a completely new thing. It was there at the beginning of cybernetics as a discipline, and what you see here is from a paper written by Doug Engelbart, and if you haven't seen this, you should go Google this. He has given the mother of all demos, basically a computer demo in the 60s that does everything that we do today. It's really mind-boggling. You should see it. But what they were focusing on at Xerox PARC to augment people's intelligence was to understand what can we do to take off tasks that are not really suited well to human mind. So here you can see a typewriter, a pencil taped to a brick, right? And this is a person typing the same sentence or writing the same sentence with the same tools. This takes 7 seconds, this takes 20 seconds, and this takes 65 seconds, right? What we are trying to do, what I mean by augmenting people, is to take something we do like this, remove the brick, and get there, or even better, get here, right? And this is decidedly different from trying to make a writing machine that just writes automatically instead of you, that you don't have to do anything. What it's doing is it's combining your best thing and some machine doing what it does best to sort of elevate both. So for example, you're drawing a circle, right? Well, you can just try to draw it like this. This isn't a great sort of task for our hand. We kind of don't do, we're all right. Here's one tool that kind of makes it much easier, right? And here is usually how you would draw a circle today, right? There are layers in Photoshop and you can move things. But my point in all of this, because I'm about to talk about generating images and why that could be really cool and useful. When you get to this stage, right, you don't have to worry at all. You don't have to spend any buffer in your mind about being careful with your lines and making sure that you got it just right. If you're at this stage, you can just draw 20 circles real quick and make something more interesting with it in a short amount of time. So Think about what we've been doing with technology. This kind of stuff has been happening, like I said, for a long time. Especially, let's focus on personal computer technologies, right? We keep augmenting the next thing so that like the plus between humans and machines sort of like elevates both of them. Okay. This is one of my favorite technologies, Ctrl Z Undo. And I think it's groundbreaking because it takes away the fear of doing something wrong with a computer. But it's also, it didn't come from, hey, this like completely new technology is of like undoing things. We discovered it accidentally, or as the next natural sort of like stage in personal computer technologies. No, it was about people's needs, understanding sort of like what kind of boost does your brain need, and then giving it to them. It's basically memory. You just save the states that are previously in memory. It's actually easy technology-wise. But figuring out the right augmentation is kind of the challenge. Okay. Let's move from this augmentation idea of like trying to get something done, like writing something, but let's also move towards creative process too. I showed you the circles. Well, if you can draw a circle perfectly real quick, then you can do a lot with them. But can machines and this like new deep learning technologies actually can help inspire us even further than that? Robin Sloan is an author, okay? And he did this. He basically built a model, let it read 50 or like, I don't remember how many, but like a lot of old science fiction books, right? And the model just like generates new sentences or just generates more science fiction text. It's just trying to come up with things that it has seen in old books, right? But here's the cool part. He made this into a plugin so that in the editor, he starts typing a sentence, okay? And then he hits a key binding, and the computer just like completes it for him. Okay, hit it again, and if he doesn't like it, he can just like keep doing this. And basically what he's doing is he's getting inspiration from this model, right? This is the system of the man and the machine, and basically plagiarism becomes a bit of an issue here. Like, okay, if they have read, like if the model has read all these books, it's not stealing a sentence, but is it stealing something? What's going on there? That's interesting. But what I want to focus on is, as these new technologies around us, all this machine learning is developing, this is actually creating a lot of really, really interesting opportunities for us to offload parts of the creative process onto a machine and actually really find our own voice, actually in collaboration with a machine. That's really interesting. Here's what he did next after this. It was raining. Cats like dogs is just the sentence. Give me another sentence. She left me forever. What it does is it's trying to, in the meaning space, fill in the gradual sentences that go from this to this. Are you ready? It's not good. So when you look at it, it doesn't feel like a very smooth transition, right? I wouldn't call this like very useful, but it's interesting, right? What we are doing is sort of collaborating with machines in creative endeavors, which is really interesting. Okay, and here is like what I want to mainly focus on in terms of this creative focus around neural networks and deep learning. So I'm going to talk about generative adversarial networks. Basically, all these faces that you're seeing, and we're going to get back to them, they were imagined by a computer. We just showed a computer a whole bunch of faces. This is what a face looks like. And then asked the computer to generate like more new faces. And these are faces, some of them nightmarish, some of them are very passable as human beings. So we'll get to it. First of all, okay, how do you get a computer to look at a bunch of faces and understand what a face is, right? Let's talk about how it works. Okay, so this is actually not a single neural network doing something. It's a framework with like two separate networks working with each other, okay? Let's call one of them a forger and the other one a cop, okay? So this is what the forger does, okay? All it does is it takes some numbers, it takes a vector, right? Don't worry about what the vector might be. It's just like 5 numbers, right? And spits out an image. If you give it the same 4 numbers, it spits out the exact same image. If you give it different numbers, it spits out a completely different image, right? But it's an image. It's an image maker generator thing. So it could also generate, I mean, it's basically pixels. It could also generate an image that looks like a face, right? Or it could generate something that looks kind of maybe like a face. Like all of these are potentials. But what it does is take numbers, give me image. What the cop does is take an image and tell me if it's an actual face or not, right? So it will look at this, think about it, and I don't think that's a face, it would say. It would be correct. This is a fake. This is not a face. Then looks at this and it says like, yeah, this looks very much like a face. And again, correct, real. And you look at it and say, is this real or not? Now, in this case, I'm also going to say fake. What I mean by real or fake is that this is an actual image of a person's face versus like some generated image that didn't come from an actual real photography like process. OK. Now, this basically forges faces. This determines if they're forgeries or not, right? That's the whole idea. We start with like just these dumb things. We didn't train them yet. And obviously, we have our millions of images of faces to show the computer, right? OK. Here's how it all goes. It's an arms race that starts with the forger sending an image to the cop. Now, the forger can either forge one itself, or it can pick one from a real image and say, hey, this is a real image. Now, this has to figure out if it's real. Did you really pick it from the real ones? Or did you just like come up with it yourself? That's what the cop has to do. So the forger starts, generates an image, not a real one, sends, hey, here, try this. This is totally a face. I took this from the real set. And the cop very proudly says, no, this is fake. The cop is correct. It understands that it's correct. Doesn't need to change anything. I'm the best cop in the world. The forger is, though, in real depression, right? Like, I am not worth anything. I am not working. This is not happening. So how is it trying to figure it out? So what it's doing is it's trying to get better at fooling it, right? Like it sort of like makes them a bit more passable. And the cop now is fooled, let's say in this example, and says, hey, this is real. Now, once it realizes, once the forger says, no, it wasn't real. I actually didn't send you a real image. I faked this one myself. I'm really proud. Once the cop learns the truth, then, OK, how can I improve myself, right? How did it fool me? How did I not understand that this wasn't real? So then it sort of changes its parameters a little bit, and then back and forth. OK, forger is happy, sends it. Now the smarter cop denies it. Now the forger needs to get smarter. So basically, these two guys are getting better and better at fooling the other one or catching the other one. Right? So you keep doing this over and over again. You keep sending real images. You keep making some. And basically, as this keeps going, the forger is getting better and better at fooling the cop, and the cop is getting better and better at not getting fooled, where it equilibrates in something like this. So, and the forger is really called the generator, because it's generating images. And the cop is called the discriminator, because it's discriminating if it's real or not. But by the end of this equilibrating, this is a pretty good generator. And this is a pretty good, like, you know, cop too. But like this one really was there to, you know, feel the mastermind evil of this guy, right? This is really what we want. We use the cop to get it better. OK, so. GANs, or generative adversarial networks. Basically, a couple of networks, one generator, one discriminator, which we trained with an arms race. But how do their innards work? What would we see if we ripped open their guts? Well, let's start with the more straightforward one, the discriminator, the cop that just has to classify an image and say fake or real. OK. Now, let's make the problem a little bit simpler while we're working on this. This is an image of an optometrist. I have an irrational fear and hatred of optometrists. So they keep showing you things like that that you can't see. But in this case, this optometrist is just a little bit extra evil, okay? Because he is trying to trick you. Let's zoom in on this. Okay. Well, you probably still can't see it. Let me zoom in more. Okay. Some of these are not letters. So this is not a letter. You're not blind. This is just a cruel joke. Okay, this is an O, X, I can kind of see the H. This is fake. C, nope, that's a Y. That's almost like something, but it's not. Okay, so basically, imagine this is what we're trying to do. Some of these are actual real letters, and some of those are not letters. By the way, all we did is it's the same problem. We just went from a lot of pixels to 3 by 3 grayscale, and letters instead of faces, but it's the exact same problem for the cop. Okay. Now, this is, of course, an age-old machine learning sort of thing to do, classification. We are going to take some images and say real or fake. Okay. We're going to train this model, and then it can basically take an image and tell us what it is. So a very straightforward, really old school, like standard way of doing classification. One of the first like machine learning things that you learn if you study machine learning is like logistic regression. Okay, basically we need to represent our image with some features, send it to a logistic regression, which will give us a probability of this thing being a real letter or a fake letter, right? So and basically. Obviously, the 50% probability is the cutoff. So if our model thinks 60% this is an actually letter, so we're going to go with like real letter. Okay, so that's how it goes. It's pretty straightforward. And what kind of features do we use though? How do we represent these images by numbers? That's actually pretty straightforward too, right? Like these are basically matrices of how dark a pixel is, right? So. And there are 9 pixels, so you can think of those as like, those numbers represent this image, okay? You give it to the logistic regression. Let's say this is an H. It does well on the reality score. 80% good. 3% not real good. But the problem with this is it cannot catch complex local and nonlinear relationships. It cannot understand all the like how all of these things intricately play with each other. It cannot extract these structures of lines crossing to make a T and an H. Like it actually focuses on like how strong is this guy here or not. So it can learn maybe like with a lot of data like very, very specific shapes, but it is difficult to capture all these nonlinear complex local relationships. So deep learning comes to rescue, right? Like what happens is you go logistic regressions of logistic regressions, right? So what you do is let's focus on local areas of an image, okay? This is called a convolutional neural network. These have been around for a while as well. We have been using them to classify images for quite a while. So what it does is, hey, okay, instead of the entire image, what if I just focused on this area, right, this window? Okay, so this guy is only going to basically represent with a single number what's going on in here. Okay, then we slide the window. This guy is focusing on those 4 features. This guy is focusing on those 4. This guy on those 4, right? And then remember, these were like this square and that square. Now I can do the same sort of sliding window of convolution by making this guy focus on these 3, this guy on these 3. Okay, so basically what we've done is we've added additional layers, and the very, very final number that we're representing is again like 0.8 or 0.3. That's the probability of the whole image being real, right? And these functions in here are basically representing something about the content of these sliding windows. That way, by sliding the windows, we can capture those local intricate sort of like complex nonlinear relationships, right? If any of you have dealt with any like natural language processing, actually the idea of n-grams, where instead of counting only the word frequencies, but actually also counting sort of phrases or multiple words next to each other, isn't that far removed from this idea, right? You basically kind of zoom in on local parts and then bring them all back together. Okay, so the one thing about deep learning, though, is I should tell, the history of deep learning really isn't like, hey, we came upon this like really simple idea and like once it clicked, it worked. It's really not like that. There's a lot of that, but also a ton of mathematical hacks and, oh, like rectified linear units work really well in this architecture. And then, well, when we do batch normalization instead of dropouts, like there are all these mathematical tricks and stuff. So part of the reason I'm saying this is if you're not super familiar with like deep learning, if you want to get your hands dirty, I would really recommend, I mean, maybe like the simple ideas from scratch, implementing them from scratch might be useful. But if you want to play with these latest sort of like technologies, it's good to take some of the implementations that already exists by people and sort of like go from there. Because all these sort of mathematical hacks are taken care of in that kind of like code base. Okay, here's how it actually looks like. This was our toy example of the letter. This is the discriminator from the 2016 DC GAN paper. One thing you'll notice is we had 3 by 3 by 1 as our initial image. This is 64 pixels by 64 pixels and red, green, blue, 3 dimensions, right? So we are basically making that 5 by 5 window that's sliding, right? Because you're sort of sliding that window, you're actually getting like a narrower, smaller one. So now it's 32 by 32. These are no longer images. This is basically, think of it as like matrices in different levels. And because in here we don't know what this number really represents, all we know is that it's about this part of the image. We don't really understand what this number is doing, but when we train the whole thing for this to work out, it works out. But it is hard to like say if during the running of this is spitting out a 5 that's going in there. What does that mean? We don't know. So again, in here, you can see this kind of almost like as a shortening and elongating of an image, but it's no longer really an image-like thing here anymore. Okay, so basically, but then we keep doing this until at the very end, we have our final basically logistic regression. It's very close to logistic regression, which gives us a single number. Take an image, single number. Okay, so this was the discriminator, how it worked. Okay, and what about the generator, the kind of a little bit more interesting one? Well, actually, sort of like what it will do is take a bunch of numbers and return a 3 by 3 by 1 matrix, right? So actually, maybe it's not that surprising, but when you look at it, there are some like minor details, but it looks almost like the opposite of the discriminator, right? Like there we started with a big image and then ended up with a single number. This is a very similar structure in terms of the matrix sizes and stuff, but we start with 100 numbers and end up with an image. And these weird things that you see is just that when you're going reverse, that convolutional window sliding becomes a bit more complicated because of like some geometric algebra thing. But basically, it is the reverse of starting with 100 numbers and ending up with an image. And I did all of this using TensorFlow. Like the code is online, you can actually go play with it yourself as well. But as I was saying, it's really useful to sort of take some actual implementations of like new papers and technologies out there. It really solves a lot of the headaches already for you. And believe me, it can still like create a bunch of headaches. And also, there are a bunch of like when I was working with these, I've actually corrected like a couple of bugs in there, which is like very normal. I'm sure I introduced some of my own. So build on top of other people's work. The reason I wanted to show this is just this part of the code. Just wanted to show you with TensorFlow like how simple it might look. That entire architecture that I was showing for the discriminator, this is the code to describe it. This is it. And this is the generator. Like you can see, it's a little bit more wordy, but like it's really a good interface where you can take like an idea like that and actually convert it into code without much difficulty. And I didn't wrote it. That was basically Taehoon Kim. And I also used some of Brandon Amos's work. OK. So I went over like how these things work, right? Like the arms race. Now I can actually generate faces that the discriminator can't even tell from real faces. That looks great. And basically, what we ended up with is a good image generator, right? So those 100 numbers, right? You can think of them as basically 100 numbers that describe the properties of a face. And our generator will take that and turn it into a face. Now, we have no idea what any of those 100 numbers really refer to or have any sense of like, I want a more glass-wearing face. I should change these numbers towards this direction. Like, without actually going deep down and creating vectors that specifically do specific transformations, that is hard to do. We don't understand what those 100 numbers are. But what we can do is, hey, now that technically any image that it creates is supposed to look like a face, we could just give it random numbers for those features and like, hey, what kind of faces does it come up with, right? So let's create a bunch of numbers, give it to them, and here are some faces that it generated for me. Again, I want to show like something like this, right? Where this is not a psychopath at all, I think. This person is melting. This is not really a person. And here again, like pretty passable. And please don't haunt my nightmares, right? I don't think that person has eyes. Okay. But anyway, the thing is, what it has learned is a lot of these complex linear relationships. Like it knows, oh, hey, this like nosy kind of thing. And it knows that there are like a million different noses. And when I say it knows this, obviously it doesn't have an understanding or a representation that we could understand. But it has understood those like local complex relationships. And sometimes it doesn't work out really well, but it still like at least has the shape of a face. And remember, I could always train this more with more images too. So this isn't like the ultimate end of the algorithm. So more images, some interesting things to note, like you can see glasses somewhere. The images, those 2 million images have people with glasses on them, but not as much, not as many as regular people without glasses. So glasses occur like not so much, but it kind of pulls them off, right? Okay. And more faces, like with the coolest sunglasses, this person wins. But OK, I didn't even begin to tell you about the cool part. Okay, so those 100 numbers, that vector representing a face, that they live in a linear space. What that means is you take those 100 numbers, right? Take one of them and very slightly change it and give it to the generator again. The face it comes up with is going to be slightly different indeed, but it will be very close to that first face that I started with. So similar vectors give you similar faces. What's even better is you can actually do algebra with faces, right? These are linear vectors that you can add and subtract from, right? You can go to this point, which represents this image, and hey, jump to that point by adding this vector or subtracting that vector. You can do math with, you know, let's take a smiling woman, let's remove the neutral woman, add a neutral man, we have a smiling man, right? Like, you can play with glasses. What's happening is, again, we don't have like these two numbers tell me what the glasses are, or like how the glasses should look like. It's not like that, but we can actually construct these subtraction and additions to basically figure out like what's missing, like what's in here but not in these, for example, right? Okay, this is fun, doing math with faces. All right, but let's get back on track because, as I mentioned before, this is all about my vanity. So now that we have a generator, okay, like what numbers would a picture of my face take? I'm kind of curious about that, right? So if I could actually take a face and go the opposite way and sort of like figure out what numbers that face actually is represented by, then I can do math with like any face that I want, etc. So great, let's get started. Here's our dilemma. This is what the generator does. It takes those 100 numbers, gives me an image. Doesn't work the other way around. We didn't train it to do anything like the other way around. So basically what you have to do is, all right, which input will generate this? Like one really stupid way of doing this is that obviously, hey, let's keep generating random vectors until we hit my face, right? Not very efficient, obviously. But so for searching large spaces, we have like a lot of optimization algorithms, right? Like, so all I have to do is, what if I started from a random face and then just push the numbers a little bit in the direction where it would make it look a little bit more like my face, right? And keep doing that and keep doing that until I get the numbers. So what I'm doing is basically giving you a bunch of numbers. You give me a face. I'm comparing the pixel values of that face with my image. And then I'm calculating a score of like how well of a match it is. And then I'm trying to get to a better match by nudging those numbers, right? Okay. One thing to note also, this works better if you don't only just try to make the exact same picture by focusing on pixel differences. You know how the discriminator is also sort of like having an idea about how real the face is? Like it will say, this is 80% a real face. I'm almost sure, right? Like that 80%, I'm also trying to maximize that so that it looks like a real face and not like one of those nightmarish creatures, okay? Because, you know, like vanity. Okay. Now, here's me telling the computer to generate faces that look exactly like these pictures of my face. Horrible lighting, all like cropped out of Facebook or something. They're different. There are some black and white, some with glasses. I'm curious how it will do. All right. Here we go. Boom. All right, no, I'm kidding. Remember how I said we will start with like completely random faces? Yes, this is not what it came up with to mimic this. So this is each of this a completely random 100 number vector. So basically a random face. It's just more random faces. But now I'm going to start nudging each of them to the corresponding one, right? Like, so this is how they change as I change the 100 numbers. Yeah. See? They're turning into me. Yeah. Except that guy. And here's one interesting thing too. So do you see this? I have glasses. And here, I don't have glasses. And I'm trying to look like Clint Eastwood or something like doing this squinty thing. But this is interesting. This is telling us, well, it couldn't replicate the glasses here, probably because it hasn't seen enough similar glasses in context to figure out like how to do that or something. But what it does is remarkable. It actually sort of, all right, gets rid of the glasses, and it still looks like my face without the glasses, which is really, really interesting. And you can also see that like these are not perfect, right? First of all, 100 numbers instead of all those like 64 by 64 pixels is much smaller. So we are actually compressing things. But more than that, basically with like the amount of training, et cetera, that we've given it, it cannot create any type of face image, right? It's sort of like limited in what it can do. And this is why there are like some of these differences in here. Okay. Now, since it worked with my face, and also, to be honest, like this, the faces that I trained it on were celebrity faces. This is a free to access academic data set out there on the internet that you can play with too. So these are all actual Matt Damon faces. These are all random faces that, again, I just randomly generated. We're going to nudge all of these into these. Are you ready for the Matt Damonification of these faces? Yes. Okay. Let's do it. Let's do it. It's working. Yes. Again, some of them are like pretty close. I think these are okay. And some of them are like not so well. But you get the idea. Finally, we can't, like if you're going Matt Damon, we can't not do this with George Clooney either. So here are Clooney's. Here are wannabe Clooney's. OK. So by this point, I have a bunch of numbers for a bunch of my pictures, for a bunch of Matt Damon's pictures, and a bunch of George Clooney's pictures. Remember, the whole idea is to prove that my face isn't that different from this beautiful face. By the way, I chose someone without facial hair, mostly to show you like how that changes and like how that affects things. And remember, for either of these faces, I now have a set of numbers that I know if I give it to the generator will create something that looks a lot like that. All right? So I know the numbers for this guy. Now the numbers for this guy. What if I actually went from here and slowly, like in 100 steps or something like that, slowly go from this vector to that vector and actually showed every single interpolated image in between, right? That way, well, the one right here, the one close to here, will be really close to this face. The one here will be really close to my face. But this should be a smooth transition. What's more, it should be that like anything in between should be able to pass as a face too. So it's not like, hey, just like fade out from this, fade into that. But everything in between needs to be a face. OK. Computer, turn my face slowly and gently into Matt Damon's. Are we all ready? This is what we've been building for, so let's go. OK, first I turn into a demon. And that's Matt Damon. Whoa. I know, right? That's what I said. OK. So each of those images that you're seeing corresponds to a different vector in between those vectors. Okay. And this was like my goal all along. Like, look how similar we are, right? But one thing I was also curious about was, OK, so all those different images, obviously, like my face doesn't have a 100 number vector associated with it. An image of my face has, right? Like obviously the lighting, the colors, the framing, everything has to do with something. Like my face doesn't have those numbers. This has a separate set of numbers. This has a separate set of numbers. So, OK, this is a linear space. So in this space of vectors that represent these faces, this lives here, that lives here, that lives here. So like, what if I found the point right in the middle, the average vector? That should be like the essence of my face, right? Like this is kind of like what is the stereotypical Irmak face shared along all those different sort of images. OK, so this is my essence. A shady goatee. Keep in mind also, this isn't that many images. I have a feeling like it would actually get clearer if I could use more than just something like 10 images for me. But this is the platonic Matt Damon, the averaged out Matt Damon. And this is the eigen Clooney. So one thing you'll notice is that these two movie stars' essences look a lot like each other's and very different from this guy. So this is the point where I was starting to get sad and stop tinkling with the GANs. But I just want to share, before we finish, I just want to share like a couple of moments that like blew my mind right after I've sort of like played around with these. And obviously we have to play this out. This is the most important slide. OK, so here's what did this to me. Now we actually did, they actually did the stacked GANs on top of each other. There are actually two stages. The first stage kind of generates a rough draft, almost like think of like a painter doing a sketch first and then putting in the details. And not only that, actually this whole thing is now coming with text descriptions. So basically, they showed it a whole bunch of bird pictures and said, this here is a blue bird with a white wing and a small brown tail or something like that, right? And here's the image. So basically, once you train it like that, you can, instead of just saying, hey, give me a random bird image by, like generating 100 numbers and turning it into an image, instead you can say, remember those coupling with the descriptions? Hey, generate images of a small bird with a white breast, light gray head, black wings and tail. And this is what it imagines. These are all, again, not real birds, completely generated and hallucinated by a computer, given this prompt, right? And it's mostly correct, right? Like, so the white breast, light gray head, black wings, yep. I find that fascinating. One other thing, by the way, a lot of birds, like this is coming from National Geographic or something, like you can see the background is blurry. That's because of those like lenses that they're using, like really, really shallow focus of depth. And it has also learned to make backgrounds like that, because that's what it's seeing, right? So remember, it is not necessarily learning what a bird looks like. It is learning what a National Geographic image of a bird looks like, kind of, too. So keep that in mind. And I just wanted to show you this thing, the first stage, second stage thing. Like it starts with this, and then in second stage it turns into that, right? Rough shapes and then details. It's really cool. And finally, so at the beginning, I talked a little bit about augmenting intelligence and what that means in terms of creative endeavors, right? Like right now, people are working with GANs, for example, in different areas such as, hey, let's generate a bunch of assets for video games real cheap or something like that, right? There are not directly GANs, but related technologies like deep fakes where they put a famous person's head onto like a porn scene or something like that. So there are like a variety of ways this is being used. But the thing that excites me the most is things like, can we create tools for creators where, okay, you want to, let's say, make a scene and quickly try different emotions. Like, is it like, what would this look like if this person's smiling or not? Or like you start with like a sentence and you could make it shorter or longer. Or in this case, hey, the different versions a molecule could shape itself, and then what the properties of that could be. So a lot of ways to take away really, really difficult tasks from people's minds, and then putting it into a slider so that they can focus on creating with those things instead of focusing on tasks that are not directly related to that creative endeavor. And this is going all the way back to removing the brick from that pencil, right? And finally, I have the image of the most ridiculous Star Trek of all, Star Trek 6. In this, they go back to the 20th century, and Scotty here is talking to a mouse, saying, like, this is how you make transparent aluminium. And then they like make some transparent aluminium and then save some whales. But what this is reminding me is that we're slowly getting there, right? Like all the minutiae of like figuring out what the molecular diagram should look like, etc. That's done by the computer in this crazy out there like science fiction campy craziness. But we are getting there, right? You can just like do this sliding, and we are pretty close to living in the future. Thank you very much.
We have time for some questions. Let's start in the back in the red.
Can you hear me?
Yes.
Okay, so you mentioned how in your generative adversarial networks that you essentially need to tweak the input images until you get something that resembles like a real image, and that's essentially a gradient. And I know that one of your first examples was with English sentences.
Yeah.
Now, I don't think that those English sentences were actually generated with generative adversarial networks, because you can't take gradients with respect to discrete items like that. So can you give some insight into how you would apply GANs or some generative network to sentences?
Can you repeat the question?
Sure. The question was, with images, for example, we have to keep making little adjustments until we find the right image. Like we have to adjust the vector to find the right image. What this means it needs to be something continuous where you could make small adjustments and the result changes slowly, so that you can calculate gradients or how things will change in different directions and basically do what we do here. So going back to Robin Sloan, the question was about, well, you can't really have gradients with sentences, so how does that work? And indeed, you basically need a continuous space. So with images, like you can have a tiny, tiny amount of difference between one image and the other one. Basically, one pixel could be slightly darker. But with words, for example, it is difficult to go from one word to the other. You're making a jump, basically. What Robin Sloan is using there, and also this has been used with like word-to-vec type of things, is that you can still assume a continuous space, and discrete things like words live in that continuous space, and you can kind of play around in that continuous space. What this means is that you make a little gradual difference and the output is exactly the same word or the same sentence. So we don't have those gradual differences, but not unlike starting with the word king, for example, and representing it as a vector, and then subtracting queen, subtracting man and adding like woman gives you queen, something like that. You can do math with these vectors. What happens with sentences or words, though, is basically you have to do subtraction and addition. Like you have to figure out the vectors and then add and subtract them. And where you end up is basically in the vicinity of a word or a sentence. And then you find the closest word or a sentence. So there is still like things we can do in those discrete spaces, not as easy as sort of like training a GAN on faces.
Other question?
Yes.
I was curious how, like, in your work with augmented intelligence at IDEO, what are some ways that you're using either techniques like this or other related techniques for this?
Yeah, good question. So at IDEO, what we really focus on is human needs, right? So in a project, for example, almost the first half of the project would be talking to people, also exploring like exploratory data analysis, that kind of stuff. But and usually we use deep learning very, very rarely, because it like really right now there are some very, very specialized, specific sort of problems which it can work really, really well in, and we can use something like that in terms of like as a intermediate process. But we did something around fashion, for example, where we took all the images of a certain year of like fashion designs, and we first used deep learning, basically already trained models for image classification to represent them in terms of like features that are meaningful. And then we basically mapped out all those images so that like similar images are next to each other. And you can kind of see on a given year like which area is crowded, what type of like styles are used a lot, as well as, ooh, there's like a gap in here. So maybe there's an opportunity to create. And in fact, not that we did that, but you could do something like, hey, this is a map with like a lot of the polka dot dress stuff here, and like these sort of like summer dresses here, and ooh, there is a bit of a gap in between. You could click here into that gap, and it could use GANs to actually generate something that would go in that part of the map for you, right? So this is one example of like how we might use these kind of things. But honestly, when I was working with this, like I said, it was this completely vanity. I wanted to sort of get familiar with the technology. It was just a fun way of playing with it. Obviously, it gives you like an idea of like how it works, and then The next time you're in an ideation session in front of a whiteboard, like with post-it notes, trying to come up with like how to do something, it just pops up and now you can do it. So yeah, long story short, we don't use these things that much yet, but hopefully more soon. Yes?
They're able to play around with sound where they get, record an actual person's voice. And then they're able to transfer that person's voice to someone else speaking using similar technology.
Yes.
And now I can actually, talk on, I watch the presentation and everything. If they can talk on the phone and actually sound like that exact person, like Donald Trump. That technology is here today.
Yes.
What about video conferencing where now I can sit in front of the computer, not only do they see me or hear me speaking as Donald Trump, but now see me on a computer screen. I am Donald Trump to them. They hear me and see me using this technology.
Yes.
Are computers powerful enough to handle that, or do we still need the supercomputer to process all this instant? Because a lot of this is showing just stationary pictures.
Yes.
But actually to show a video.
Yeah. So that kind of stuff, which is like where they're transferring one type of movement from one source to the another. Yeah, they have been working on this. It is like now working really, really well. And very, very soon you could just do it like on your computer too. Like in fact, I bet it's going to be like on, there are going to be filters on Snapchat and like the Donald Trump like filter. I don't know if that's going to happen, but those like on Zoom or Google Hangouts, you can like click something and it gives you like a little funny hat or something like that. So basically, it's just an extra like that is getting way better is basically what's happening. But I also wanted to mention another thing. There's also a lot of worry around it, right? Like so you can fake, this complete other person. But to that, I feel like Photoshop has been around for a while. And, like this has been, Photoshop is like a part of our, language now. We understand it. I know this is shop because of the pixels is like something else, but, so we have biases around it. We have different mechanisms around it when somebody's like voice today, like when tapes get released, for example, people still say this is manipulated because it is possible to manipulate and edit them, right? So it's not like suddenly we have a whole bunch of new technologies and we don't know what's real anymore. I feel like this is just an extension of this type of mimicry that has been in our lives already. We just have to adjust and get used to it.
In the back?
When you were talking about, you showed the average of all of your faces, like in this case, the trained GAN. You had said that you thought if you had more examples of your face, that the average would become clearer. And given that you're searching through the space of an already trained model, this seems very counterintuitive to me. I was curious if you could explain more why you would expect the average to become sharper with more samples.
Sure. Think of it like, so if you actually do this in pixel space, like you take all of my images and average them, that still looks like an average face. And it actually sort of looks a bit unlike you, like things get more symmetrical and then you suddenly stop recognizing yourself and stuff. But with that, if you average like more images in pixel space, things get clearer. Mostly because if you just take the pixel averages of like two things, like two images, it's going to look like ghosty because things like one nose will be here, the other one will be right next to it, and you'll be able to see it. But if you superimpose like 1,000 images, right, like it will be kind of like quick sketching where you go over the same line 100 times and now it looks right, even though maybe none of the individual lines look right. So I'm still talking about just averaging all the pixels of my faces. I'm not talking about vectors or anything like that. But just because these are different images with, like, it is not only capturing what makes my face, it is also capturing, am I looking that way? Is it like black and white? Like, is the light hitting me here? So if you had more of those, the parts of that 100 number vector that deal with that kind of would get rid of itself through noise, hopefully. And then the things that are more about my face would be left because those exist on every single vector. But the little noisy things that can make things blurry are not the same on every single one. So the more vectors you have, the better it is. It's not that it has learned my face or anything. Like you said, it is not learning my face. I'm just saying if you average more things, you know, the noise cancellation will make the thing sharper.
Maybe time for one more question. Brian?
What made you pick GANs over something like a variational autoencoder where people are specifically trying to interpret the
Yes. So the question was why GANs and not something like variational autoencoders or other generative things. And it's true, GANs are not the only they're not even the only deep learning based image generation framework. I wanted to play with GANs mostly when they came out, in 2016, they were everywhere, and then people have been working on them and improving them with different sort of loss functions and stuff. I just wanted to really get familiar with it. I was already kind of familiar with what autoencoders can do, and for others, if you don't know, autoencoders are very similar, but a single network that is again wanting to create images. It starts with an image, right? Let's take my image. We start with it, turn it into 100 numbers, and then blow it back up to itself. So it's kind of like, hey, if I compress you into these 100 numbers and then blow you back up, which compression scheme will give me the best reproduction at the end, right? So I'm trying to basically figure out how to represent this image in 100 numbers so that I can create it from representation again. So it's another method. And then you just train it. You do it with, again, millions of images, and it learns how to represent that. What's even better, it actually does go both ways. You could give it an image and get numbers, or you could give it numbers and get an image. So, but they don't look as convincing as GANs in some cases. Obviously, this is a subjective remark, but people have been coming up, like I said, with interesting loss function formulations, which do tend to correlate with how we also think of an image's quality, and GANs have been doing better. So new technology wanted to learn it, and they're interestingly different than other images.
Great. So I've definitely learned a lot today, and I hope you did as well. So let's give Irmak another round of applause.
Thank you very much.